Assalamualaikum and good day. My name is Muhammad Saiful Badefri. Today I will explain about the tutorial question 1. Okay, based on this slide, the graph on the left is the hypothesis graph and the Y is the output for the hypothesis. And the right graph is the cost function and the J theta is the cost function that based on the hypothesis. Thank you.
We start gradient descent from point A, and after one iteration of gradient descent, we may end up at point B. The other side of the ellipse, then another step of gradient descent may end up at point C, and then following by other. With each iteration of gradient descent, we move toward the local optima with a down oscillation. This is the local optima. If we use larger learning rate, then the vertical oscillation will have higher magnitude. So this vertical oscillation slow down our gradient descent and prevent us from using much larger learning rate. There are two important drawbacks with our learning rate. If we choose our learning rate too large, then there are a problem of overshooting and not achieving our desired convergence point, global minimum point. At the same time, if we choose our learning rate to be too small, then it may take a lot of time to get the coverage point, which is not very time consuming, but we still could reach our global minimum.
And next is for week number 6, tutorial question 1. Why the learning algorithm will suffer during the training when features are not scaled accordingly? This is because if the x1 is larger range than x2, it takes that the contour of the cost function j of theta a skew elliptical shape. And when run the gradient descent on this cost function, it can make the gradient descent a long way of time before to get to the global minimum. So to make gradient descent run much faster and converge a lot fewer iteration, we need to scale the feature accordingly and it must not too large and not too small a range.
Hello, today I will be explaining about cost function. As we all know, linear regression cost function is represented by this equation to and it is representing the square area of the hypothesis function and the target y. For logistic regression function, we can divide the equation into two, where y equals to 1 and for the equation negative log h of x and y equals to 0 for the equation negative log 1 minus h of x. To reinterpret the equation, we can see from this graph where h of x is to x-axis and cos is the y-axis. From the graph, we can see that when the actual target of y is equals to 1, the hypothesis is also equivalent to 1. The cos will give a value of 0. That means that the prediction is correct with accordance to target y. On the other hand, at the opposite direction, which is this, as the h of x goes to the value of 0, the cos will become larger, and it may go up to infinity as it draw closer to 0. It means that we have to penalize the algorithm with a very large cost when there is an error. For the equation of negative log 1 minus h of x, in the case of y equals 0, we can see that there's another line which is the opposite of when y equals 1. This line is representing the equation and it's the total opposite of the previous equation. From this equation, from these two functions, it can be simplified into one general function, and the function is given in equation 4.1, which is here, this one. So in the case of m number of data set, in general, the cost function of logistic regression will be written as follows, as this equation.
Hi, I am Wani. I want to show you the main equation behind how regression works. Now, if we were to feed a algorithmic function to this data, it gives us a pretty good fit to the data. Then, feed an overly high order degree polynomial, we end up with a curve that may fit the training set very well but overfit the data. Suppose we penalize and make theta 3 and theta 4 least more. This is our oscillation problem. We must minimize our user square error cost function. Next, take this objective and modify it and add this. Choose 1000 as some huge number. Then we minimize the function. So when we minimize, we can get the new function. We are going to end up with the theta 3 close to 0 and theta 4 close to 0. And then we're getting rid of these two terms. Next, this term. So we only left with a quadratic equation. Lastly, we end up with a fit to the data, so can no quadratic function plus maybe tiny contribution for small term. Theta 3, theta 4, that is maybe very close to 0. Then end up with essentially a quadratic function. This is the best good. Next. So, how overfitting with linear regression for housing price? First, fit a linear function to the data that not a great model is underfit and height bias. So, give fit a quadratic function, it works well. Next, fit a 4-order polynomial, the curve through of 5 example. That's a good job fitting the training set, but fitting the data given not a good model. It is overfit and this algorithm has a high variance.